Hello, welcome back everyone. So this is a really important supplemental video where we're going to be talking about indexing equations and more importantly, or more specifically, how do we use subscripts in equations, okay? So this is often confused but very important point both in mathematics in general and specifically in MATLAB coding, okay? So I'm going to talk about the various ways in which we use subscripts and indexing of equations, because really we use this subscript to mean many different things on any given day, okay? So just to start, oftentimes we will look at an iteration equation. Okay, this is an iteration equation, xk plus 1 equals a times xk. So each of these x's may be a vector, and this a might be a matrix. And so this index k is my iteration number. Okay, this is my iteration number. And it tells me that I go from x at day 1. So I think of this maybe as iterating in time. Maybe a takes me from my state today to my state tomorrow, and so on and so forth. So x1 goes to x2, goes to x3, dot, 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 to xn. This would be my day 1, day 2, and so on. Okay, day 3, dot, dot, dot. So this index here might have a physical meaning that this is the day, right? x1 is my state x on day 1. x2 is my state x on day 2, and so on. Okay, so this could mean an iteration number. We could also use subscripts when we're talking about data vectors. Okay, so here, let me draw this in red. So here we just have some curve, some function over some variable. I'm just going to say this is f over a variable. Maybe it's either time or space, t or x. Okay, and so what we're going to say is that we have data at each of these discrete points. Okay, and we're going to say that this is f0, f1, f2, dot, dot, dots. So I could say f1, f2, f3, or f0, f1, f2. It doesn't matter if I start at 0 or 1. Mathematically, MATLAB has to start its indexing at 1. And this is my function at time t0, or x0. And this f1 is my function at t1, or if we're using space, then at x1. T2, x2, dot, dot, dot. Okay, so we could say that fk is equal to my function evaluated at, for example, xk, if we're talking about f of a spatial variable x. Okay. Also, oftentimes we'll say that these are separated by some delta t or delta x. So oftentimes my samples come evenly spaced in either time or space. They don't have to, but they often do. Okay, and so I would say that I have some vector f, which is equal to f0, f1, all the way to fn. Okay, so the subscript could represent the element of a vector, and that element could correspond to which time or location that data was collected. Okay, so these are two interpretations of indexing. We could use indexing for iteration equations. We could use indexing to specify which time or which location data was collected. But we could also use indices for specifying systems of equations, ax equals b. So here I have explicitly written a big A matrix, right? This is big A, it's a matrix, times a vector x equals my vector b. Okay, and we notice that the subscripts here tell me which elements I'm talking about. Okay, so I have A11, 1, 2, dot, 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 all the way up to 1n. The second row is A21, A2, 2, and so on. So the first element, A, I, J, I tells me which row, and J tells me which column. Okay, so that's kind of nice way of indexing matrices. Now, what we can do in this system of equations, AX equals B, what we can do is we can say that if we look at any given row, that is actually an equation, right? If I take my x vector and multiply it by A, I take this column vector x and I multiply it by the first row, and that equals B1. I take my column vector x times the second row of A, that equals B2, and so on until this column vector times any row, the jth or the ith row, is equal to Bi. So we can look at a particular row equation using these indices. So look at a particular row. Okay, and what we're going to get, in fact, look at the ith row. And we're going to get that AI1 times x1, right? This ith row times x is A times AI1 times x1 plus AI2 times x2 and so on equals BI. AI1 x1 plus AI2 x2 plus dot 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 all the way up to AI n xn equals BI. This is my ith row equation in AX equals B. And I can write it using these indices here, okay, of x and A and B. So another way to write this is the sum from j equals 1 to n of A ij times xj equals bi. Okay, so I'm just summing over all of my j's, right? 1, 2, dot, dot, dot to n, from 1 to n. Okay, and the last thing I want to show you is how, if I look at a particular row equation for a specific matrix, I can write this in terms of a very simple subscript equation, sometimes called a difference equation. So let's say I have a particular A, and let me just pick one where it's 1s on the diagonals, -1 on the off diagonals, 0s everywhere else. And then let's say that it's 2 right above the diagonal. Good, okay. So my A matrix is, on the diagonal, it's just 1s. Just below the diagonal, it's all -1s, and above the diagonal, it's all 2s. And everywhere else, it's 0. Okay? So the way that I can write a generic equation AX equals B with this specific A, if I look at any kind of middle row here, what we have is really -1 minus. Okay, let's look at the kth row. So on the kth row, we have a 1 on the diagonal. So x times that, there's going to be an xk. So I have an xk. I have a minus xk minus 1 minus xk minus 1. I'm going to have a plus 2 xk plus 1 plus 2 xk plus 1. And this is the kth row, so it's going to equal bk. Okay, so I can write my matrix system of equations in this simple way if my A matrix is somehow sparse or only has a few kind of diagonal terms that are non-zero. Okay, so this is just a look or an overview of some of the ways that we can use indexing and subscripts in this class. Anytime you see an index in a mathematical equation, that means that you can vectorize that in MATLAB. You can represent that data as a vector or an array. OK, so that's all for now. Thank you.